Here we have the lecture on 4.4, which is all about evaluating our trig functions at any given angle. Now, this is still without a calculator, although we'll use it a little bit. And this is going to be using our special right triangles, using trig functions with right triangles in general, the unit circle, knowing the values, the tables, using all that kind of together to help us find these functions at any value. So starting at the top of that page, two kind of helpful things. One, we've seen something like this. It's just kind of helping us define what we mean by our theta right here. So if I give you some ordered pair, say x comma y, we know the cosine is going to be a combination of the x coordinate mixed in with that y coordinate. And then where this was typically a unit of 1 for the unit circle, also for this triangle, it's our radius. So we've seen this before, just kind of redefining those relationships generally. Now, something we haven't seen, but we have talked about, is this over here, which is a nice little guidance. It's just reminding you, hey, in any of these quadrants, what are the signs of our values? So obviously quadrant 1, they're all positive. We know in quadrant 3, it's a negative cosine, negative sine, but the ratio of those negatives gives us a positive, hence positive tangent. So this will be something kind of helpful coming into play. So let's do some examples of just finding some of these right now with everything we know so far. So if we're given a point, so we know this point's on the terminal side of theta, so similar to what we had drawn up here, if we have some theta, this point is on that terminal side at -2 and +3. Again, whenever we can, it's good to draw pictures. And I know this is on that terminal side of our theta. Now, how do we find sine, cosine, and tangent just based off that? Because that's not on the unit circle. So what we're using is this idea of how we visually see the unit circle, but as I kind of sketched up here, we're going to be tying in that idea of right triangles as well. So from the reference point of kind of this extra little angle in here, not the original theta, we're going to do our trig functions using this triangle, but the trig functions in this triangle are going to be the same exact for that angle theta. And again, we know we went -2 to the left, up 3. And then if we need to find the radius, every time we have 2 of our 3 sides, we can do Pythagorean theorem. And with these two, we'll see we get square root of 13. Now, reminder, the hypotenuse here, or these terminal sides, will always be positive because we're going to be squaring both of these. So even if we have that -2, it gets squared, we lose that negative. So the hypotenuse is always going to be positive. So now we want to find sine, cosine, tangent. So sine of theta, this blue angle theta, we could find it if we knew what that angle was, or tying in with our right triangles, although it's not a special right triangle, from this viewpoint right here, we can see that sine is going to be 3 over square root of 13, or when we rationalize that, 3 root 13 over 13. Now again, this angle, which we're using kind of as a reference to build this triangle, is going to have that same trig value from inside the triangle. So we move on, we got cosine. Cosine of theta is now going to be dealing with adjacent to this little reference point over hypotenuse. Again, we want to rationalize, that'll be -2 root 13 over 13. And we should expect it to be negative, right? As we see up here, cosine to be negative in quadrant 2. And then tangent, that's a ratio of these two. But since we have the right triangle, instead of having to do a ratio here and have things cancel, we just have opposite over adjacent. So now as we move on to number 2, it's a little bit different with what it's giving us. So instead of giving us the ordered pair of a point, it's telling us, hey, I have a theta for you. and I'm giving you what sine is of that theta. But it's also giving us one more thing. It's giving us the sine of tangent. So here's why that's important. Sine of theta being 4/5, well, that could be a theta somewhere in the first quadrant or also in that second quadrant, right? Because sine is positive in our first two quadrants. But we want to find the sine where tangent is less than 0, so tangent is negative, and that's in our quadrant 2. Let me center that out. So knowing that, we know we have an opposite side of 4, hypotenuse or radius, right, that we had here of 5, and it's going to be in quadrant 2. So we know it's going to be 4, right, as your opposite side, over that radius of 5, and this is going to be our theta. Now, just like above, instead of using whatever this theta is, I'm going to finish off that triangle and kind of use this little angle in here as my reference point again. Now, some of us might recognize it. Special triangles are 3, 4, 5 triangles is a special triangle, or 25 minus 16. Take that square root, we get 3 for that side. Now again, we're using this right triangle instead of just trying to guess whatever that angle might be, and those values are still going to be the same for our trig functions. So we want cosine and tangent. So for cosine of theta, it's our adjacent side over hypotenuse. We might typically do 3/5, but there's one detail missing. Although when I do Pythagorean theorem here, and I do 20 square root of 25 minus 16, that's square root of 9, which is 3, this was in quadrant 2, so this 3 needs to be negative. So that's kind of the real kicker here when we combine all these methods together, is making sure our signs are correct regardless of that Pythagorean theorem. So that doesn't make this 3/5 for cosine, it makes it negative 3/5. And then equally for tangent, instead of being 4/3, we're going to bring that negative with it, so negative 4/3 for tangent. So number 3, extremely similar to number 2. We're given a cosine, so that's our opposite side over the hypotenuse. We're given the sine of tangent, and we want to find some trig functions from there. So I'm going to have you guys give it a pause and give number 3 a shot. So as you come back, I have that triangle kind of drawn out for us. So we have some angle theta, so cosine, which is positive, and cosine's positive in quadrant 1 and quadrant 4, right? Just where x would be positive normally. So that's 2/3. 3 is our hypotenuse. So it's with this tangent again being less than 0. That's telling us, are we in quadrant 1 or quadrant 4? Well, tangent is when we have opposite signs for sine and cosine. So that puts us in quadrant 4. So when we do that, we have our 2, that's our adjacent side, this little reference point, over hypotenuse 3. And then we do Pythagorean theorem, but again, this is going to be square root of 9 minus 4, which is square root of 5, but we need to remember to bring in that sign with us, right? Because we need to remember to have that negative for that y value as we're in quadrant 4. So finding cosecant and cotangent, cosecant again of this whole angle theta, we're just using this little reference point in the triangle to still find that equivalent value. Well, cosecant, instead of being opposite over hypotenuse, it's hypotenuse over opposite, but we need to remember to rationalize that. So we have that 3 over negative root 5, or multiply top and bottom by that root 5. Then we have cotangent. Instead of being opposite over adjacent, we have that flipped. Thus, again, we need to rationalize, giving us a negative 2 root 5. Clean that up over 5. So if I give you, whether it's just a random ordered pair for theta on its terminal side, or I give you the trig function itself and just a sine of that one of those functions we have, then we're able to construct a triangle in one of our four quadrants. And again, tie in that ability of using the unit circle for the quadrants, and then tie in the ability of those right triangles, Pythagorean theorem, to find our functions for theta. Now, if you notice in these three problems, at no point did we even know what theta was. We didn't have to find it. We didn't even use theta itself in any of these. We kind of just used theta to get this triangle created, which we're going to see is a really helpful tool. But before we dive into that, kind of just want to make note of a few kind of common and known values. Now, again, I'm going to do this using a little sketch. Again, we have unit circles, right triangles, calculators, all that jazz. But just a couple functions about our quadrantal angles, and those are the angles on the axes, so along the x-axis or along the y-axis. So 3 pi over 2, well, there's pi over 2, 2 pi over 2, here is our 3 pi over 2. And if we're dealing with sine here, we see we haven't gone to the left or right at all, right? So cosine doesn't exist, but the sine here is everything, right? If that's going to be our terminal angle. So we know our sine there is -1. Now, we have cosine of 90 degrees, hopping back to degrees. Here's 0. That's up to 90 degrees. Now, if this was sine, kind of counter to here, right? It's strictly a terminal side that's straight up and down. So it'd be all sine, no cosine, because we're not left or right at all. But it's asking for cosine, so it's actually the opposite. Are we to the left? Are we to the right? Just like on that unit circle, our cosine here is 0. And then we have 3 pi we're talking about, and then we'll get to the tangent. So we start at 0, we have 1 pi, 2 pi, 3 pi. So it's really asking about tangent out here at pi. And again, from unit circle, we know that's cosine of -1, right? That terminal side out here. But it's not up or down at all off that x-axis. So it's all cosine, no sine. So we have 0 sine over that -1 cosine, or 0. So knowing these quadrantal angles is really helpful sometimes, because if we're given something like that, and we saw that before with either right triangles or the unit circle especially, that our sine, cosine, tangent are 0, 1, -1, undefined, kind of those specific values. But now we're going to dive in a little bit more of what's so special about these triangles and kind of using this little reference point of an angle instead of our theta in general. As we get onto that second page, we see the top of it, we're given a definition. These things that we were using weren't just reference points or a nice thing to use or a random angle. We call these reference angles. And ultimately, they're the acute angle, which lets us make those triangles, that's formed by the terminal side of theta and then the horizontal axis. So if you notice on that first page, we either drew that triangle down from that terminal side to the x-axis or up to the terminal side to form that triangle. So we have 3 examples here. If this was our angle theta, the reference angle, or the angle we kind of use, right, to make that right triangle, was this angle right there. And then the sine, cosine, and tangent from this point was the exact same as we saw over here. Now, the one thing to remember, right, we had to include sines when we made those triangles. So we'll keep that in mind as we move forward. So again, if this whole stretch is our theta, then we need to move up to form that right triangle with that x-axis again. And then this theta with the tick mark, we call that theta prime. That theta prime, or reference angle, is the angle we use. And then lastly over here, we again move either up or down till we hit that x-axis, make that right triangle, and we have our reference angle in there. Now, some may have seen this before. Sometimes I call it the butterfly trick, just to kind of remember. wherever we're dealing with reference angles, we're either moving up or moving down from that terminal side. So all of those angles or triangles have to fit within this kind of butterfly or bow tie right there. So we have no triangles that are formed by connecting with that y-axis. And why is this important? Well, the nice thing about it is instead of dealing with some larger angle, kind of similar when we did the periodic angles, right? So we had something like find the cosine of 9 pi. We didn't go around over and over and over. We really dealt with finding the cosine of pi instead. So that's a similar idea of using a reference angle. Those were just very specific cases. And this is going to allow us, again, smashing those ideas of the unit circle and right triangles to combine those together to, no matter what we're given, find those trig functions. So first, let's find some reference angles and kind of get that practice down. Again, I'm drawing a picture for everything I'm doing for this lesson today. So we got some stuff in degrees, a couple of things in radians that we're used to with pi, and then over here we have this in radians in a simplified format, right? So that's when we do that approximation. So theta of 213 degrees, I want to find that reference angle. Well, 213 degrees, where does that land us? If I started here, that 213 degrees, a little more than 180, is landing me somewhere out there. Which means as I move myself up to kind of form that right triangle, the theta prime, or that reference angle I want to find, is this little one right there. That's that theta prime I'm looking for. Now, before we find it, I'm just going to give you guys a tip right away on a fast way to approach this. If our angle we have is in quadrant 1, well, then it's its own terminal angle, or it's its own reference angle. So theta prime is just theta. If it lands in quadrant 2 from up here, right, this little reference angle is just that top half minus our original. So over here, that's just 180 minus our theta to get theta prime, or to get that reference angle. Similarly, for quadrant 3, that's going that full half and then whatever extra it is. So for there, it's whatever our actual angle is minus 180, or minus pi if we're in radians. And then lastly, if we're in quadrant 4, it's just taking one full rotation and subtracting theta to get that leftover, which is 360 minus theta. So that can be in degrees, or we can translate that over the radians, but that'll help us every single time with finding a reference angle. So for number 7, 213 degrees lands us in quadrant 3, which means we need to do 213 minus 180. And if we do that, we get 33 degrees for our reference angle. So if I were to do sine, cosine, and tangent of 33 degrees and keep my sines in place, right? So negative cosine, negative sine, then finding sine, cosine, and tangent of that 33 will be no different than finding it of that original 213. So we move on. For number 8, 14 pi over 9 lands us a little more than 3/4 of the way. So that is our entire theta, which means to find our reference angle, or theta prime, we're just going to subtract that from 360, but in this case, we're going to subtract it from 2 pi. If we find a common denominator, we're going to end up with 18 pi minus that 14 pi over 9, and we'll get 4 pi over 9 as our reference angle right there. Now again, I can then work with this smaller angle, this angle between 0 and 90, and then all I have to worry about is making sure I have the signs correct. So in this case, I would have positive cosine, but negative sine. So give it a pause, give number 9 a shot. Very similar to 8, right? We're just in radians. And then we'll come back and we'll do 9 and 10 together. All right, hope you gave it a pause. Number 9, 4 pi over 5. It's almost 5 pi over 5, or almost 1 full pi, but not quite. That puts us in quadrant 2. Now in quadrant 2, to get that reference angle, we're going to subtract it from 180. But for us, that's subtracting it from pi since we're in radians. Again, get that common denominator, and we end up with pi over 5. So that little theta prime in there is just pi over 5. Now, so far we're seeing any angles, and we'll learn kind of more in the coming chapters how to deal with all of these as well. But if any of these reference angles became, what we're kind of seeing on this table down below, one of our known values, instead of dealing with something that we may not have memorized, we can work with something in that first quadrant and just apply the signs to it. And we're going to see that's what the trick is. So lastly, number 10, dealing with radians. Our initial side, right? Radian of 1.7. Well, 3.14 is an entire half circle, right? Because that's pi. That's our pi right there, 3.14, the 1.7. So we're a little past the halfway point on that. So that's our theta, our 1.7 radians. Which means, again, we're in quadrant 2. When we come down and make that triangle, again, we're always either coming down or moving up to make that triangle. At no point are we moving into that y-axis. And then again, in this case, if we're in quadrant 2, 180 minus theta. So 180 minus 1.7, not 180, right? If we're in radians, we would typically do pi, but if we already have it approximated, we can do 3.14. So that's our 180 right there, or our pi. And we subtract 1.7 from that, and we end up with 1.44 radians. So again, the nice part about all of this is instead of having to memorize a unit circle, once we can get that little triangle constructed, we can then use Pythagorean theorem, and we can pluck all 6 of our trig functions from having that completed triangle. So let's kind of see that done. So as we move down to the bottom, we have a couple problems, and thankfully we have this table above. Again, kind of just throw in your face one more time of, hey, 0, 30, 45, 60, 90, these are real common. 180, 270 as well, but this 0 to 90, that first quadrant right there is really common, so it's nice to have those values in front of us. So here's my trick and my steps kind of for all of these. What we just did, finding reference angles, should always be the first step. So number 11, instead of even dealing with the idea of cosine, I just want to look at 4 pi over 3 and find its reference angle. So 4 pi over 3 is a little past that halfway mark, right? Because 3 pi over 3 is that top half. So that whole piece right there is my theta, which means when I connect that down, connect that up to the x-axis, and I make this little triangle, this theta prime right there is my reference angle. Well, we're going to take our original, right, because it's in quadrant 3, and subtract 180 from it, or subtract pi. So we get that that theta prime right there is really a pi over 3. So here's where this table or the unit circle kind of starts to come in a little bit more. My reference angle is pi over 3. Well, what do I know about cosine over here? Cosine of pi over 3 normally would be in quadrant 1, but what quadrant are we in? We're in quadrant 3, right? And what do we know about cosine here? We know cosine is going to be negative. So this tells me that cosine here is negative. So what I really have to do is find cosine of pi over 3. Would you look at that? We have a nice little table for us. We got pi over 3. We have cosine, which is 1/2. If it were in the first quadrant, and then all we have to do is apply the appropriate sign. So our appropriate sign here is going to be negative. So this is negative cosine of pi over 3, right? The negative coming from quadrant 3, or just negative 1/2. So without a calculator, without having to even memorize the unit circle, all we really needed was to know the cosine, sine, or tangent of anything in that first quadrant and just apply the appropriate sign. So I'm going to have you guys try number 12, and then again, like normal, we'll come back and we'll do 12 and 13 together. All right, so hopefully you pause, give number 12 a shot. Number 12, let's give it a go. 7 pi over 4. It's almost 2 full rotations, which would be 8 pi over 4. So that does put us in here into quadrant 4. I'm going to scoot this down. So if that whole piece right there, right, so that's my theta. That's my 7 pi over 4. I don't want to use 7 pi over 4. I want to use that reference angle, which is this extra little bit right there. Kind of color that one in too. Now that extra little bit, if it's in quadrant 4, we're just removing our angle from 2 pi, from one full rotation. Well, 2 pi minus 7 pi over 4, you get the common denominator. You end up dealing with a theta prime, or a reference angle of pi over 4. Now again, what are we looking for? We're looking for sine of 7 pi over 4. Well, we can already tell what sine is going to be in quadrant 4, right? It's down below the x-axis. So that tells us here that sine is what? Sine is negative. Again, if we don't have that memorized, we can think back to unit circle. Sine is acting like y. It's positive above the x-axis, negative below. But we also have that little guide on our first page here too. Well, if sine is going to be negative, then here's what we know. We know the sine of this larger angle is equal to the negative of the sine of this smaller angle, the pi over 4. And now this is one of our known angles, right? This is one of our key ones, 30, 45, 60. Those are the key ones. If you don't have it memorized, unit circle, or we got the table above, we're looking at pi over 4. We're looking for sine, root 2 over 2, but again, it's going to stay negative. Now again, on every single one of these, I am sketching something out. I'm getting that visual down. It helps me find what quadrant I'm in, helps me define my signs of my trig functions, and then after that, it is just either referencing that table or that unit circle. Now on to 13. 13 is a little bit different because we're doing cosine of a negative 120. So if this is our initial side, positive 120 would land us in quadrant 2, but negative 120 land us in quadrant 3. Now again, first step, let's get that reference angle. So we're either moving up or down to create that right triangle. We want to find this reference angle. Well, this one's not too bad, right? How much more would it take to get to a full half rotation? We're only off by 60, right, to get that full half rotation. So our reference angle is going to be that of 60. And we're in quadrant 3. So reminder, quadrant 3, if we're finding cosine, we're always dealing with something negative. And you don't have to write this piece down below. I'm kind of just using that as a guide for you, kind of help you out. So now we're really just looking at, hey, cosine of negative 120 is going to be the negative cosine of our reference angle of 60 degrees. Well, what's cosine of 60 degrees? We have our 60 degrees. We're looking down at cosine, which is 1/2, but again, it's going to be a negative 1/2. So before we move on to that third and final page, remember, every time we're doing this, just like we do with the periodic stuff, we kind of removed full rotations until we were within just that unit circle. Well, now we're going even finer tuned than that. we're really removing as much as possible until our reference angle would be something from that first quadrant. So this is kind of a callback when I said, hey, if you memorize that first quadrant of the unit circle, it comes in really handy. This is exactly why. So if you get that first quadrant down and you use these reference angles, and we're using special triangles as well, then it helps a ton with getting this done. So keep that in mind, move on to that last page. So as we come onto that last page, we got two more similar idea with how we're finding and using reference angles. And then we have a next one, number 16, that's a little bit different, but kind of ties into our first page. And then we'll have a little more practice with calculators. So 14, 15, again, reference angle is always the first thing we got to do. So 11 pi over 6, that's almost one full rotation. So that entire theta right there would be our 11 pi over 6. Make that right triangle. Now to finish off that full rotation, how much more do I need? Well, I just need a pi over 6. So my theta prime is a pi over 6. Now I'm going to actually scoot over to 15 and do its reference angle at the same time. 5 pi over 3, very similar, right? We're just missing that extra third. Just like with number 14, we're missing that extra little sixth right there to get that full rotation. So this also lands us in quadrant 4. So there's our entire theta. Again, we move up, and that's going to be our theta prime we're looking for, that reference angle. Well, how much more do we need to end up get with a 2 pi or a 6 pi over 3, just that extra pi over 3. So this is, for both of these, dealing with quadrant 4. For 14, we're dealing with tangent. And for 15, we're dealing with sine. So I'm just going to make note of the signs of those, right? Positive or negative. Tangent. Now here's an easy way to remember tangent. Tangent works with opposites. In quadrant 1, it's sine over cosine, but they're both positive, so tangent has to be positive. In quadrant 3, we know that it's negative cosine, negative sine, negative, negative gives us a positive. So we know 1 and 3, which are opposite, it's positive. So then 2 and 4 has to give us a negative tangent. Now for sine, sine is positive above the x-axis and negative below. Quadrant 4 is below, so that's also going to be negative. So it's going to let me rewrite my originals in terms of my reference angles. So tangent of 11 pi over 6 is really just the negative tangent of pi over 6. And sine of 5 pi over 3 is really just negative sine of pi over 3. Well, again, whether we have it memorized or we can use that table on the page before, the unit circle, tangent of pi over 6, that's root 3 over 3, but it's going to stay negative. Negative in there. And then sine of pi over 3 is root 3 over 2. But again, we're going to keep that negative. So that first page, I had that little table, that little graph, right, of where sine, cosine, and tangent is positive, negative. It's nice to memorize, but the big thing is sine, start there. Sine is positive where y's are positive typically. So positive up, negative down. Cosine with x, positive cosine, negative cosine. And then tangent is where the signs are the same. So quadrant 1 and 3, positive tangent. And then here we have opposite signs for cosine and sine, so negative tangent. Again, you get those reference angles, and we're just really dealing with the trig of that first quadrant, and it's just a matter of a sign change. So now we're going to use a little bit of trig identities to evaluate some functions. So we know theta is going to be in quadrant 3. So let's start there. I know some theta is in quadrant 3. So that entire piece right there is my theta. And it gives me a sine. So if it gives me a sine, instead of using that, I'm just going to be, again, dealing with reference angles. But the issue now is I don't know really what this theta prime is yet. But I do know something about it. I do know that sine of this whole large angle is negative 4 over 5. So I know it's a negative 4 over 5. So now hopefully this is starting to look similar to the very first page. So when we complete that triangle, we can use Pythagorean theorem to finish it off, use that identity, and then that lets us find our cosine and tangent. Now, reminder, and I'll kind of write this out this time, Pythagorean identity, or Pythagorean theorem right over here, we're going to end up with this side x. It's 5 squared plus negative 4 squared, minus negative 4 squared. So we have 25 minus 16. We end up with the square root of 9. And there's one detail I missed. See if you see it. We got to be having that negative 3. Why negative? Because we know that that cosine or that x value here is going to be negative 3. So now at this point, using the identity that if we're looking at sine, cosine, tangent of theta, it's the exact same if we use that reference angle, as long as the sine stay the same. That makes it easy for us. Cosine, negative 3 over 5. And then tangent, we have negative 4 over negative 3, or 4 over 3. Now, lastly, that brings us to number 17 and number 18. And this is just a big reminder about keeping your calculator in the right mode. Now, as you notice, 99% of the time, our values we find are left in exact forms. So calculators don't help necessarily up with this, but all of our other methods do. When we get really goofy angles that aren't kind of one of our known, that's typically when we rely more on that calculator. And that big reminder for us, so we'll get it in here, is just to be checking our mode. So as we see for number 17, we're going to be in degrees. Number 18, we're going to be in radians. So reminder, go into mode, go down 2 clicks, and make sure you're in the right mode before you do anything with the calculator. For this, we got to switch to degrees. After that, once you're in that right mode, all you got to do is our trig functions. We're plugging it in, and this is just another little bit of practice with us. If we do that tangent of 119 degrees, we get about negative 1.804. Then we need to switch that mode over back to radians to do the cosine of pi over 5. Again, not one of our known ones, right? Not pi over 3, pi over 4, pi over 6. When we do this in the calculator, we get approximately 0.809. So just an extra big reminder, proper modes for when we're dealing with calculators. And that wraps up our 4.4.